In this video, we will work an example evaluating the work done in a polytropic process. For this problem, the polytropic constant will be 1. Recall that when n equals 1, we have a constant temperature, or isothermal process. Let's imagine a piston cylinder apparatus and an internal combustion engine. Air is ingested into the cylinder at an atmospheric pressure of 1 bar absolute. The ingested air is at a temperature of 20 degrees C. The initial volume is 1 liter. Fuel is injected but not burned. The piston then moves, compressing the air to a final pressure of 9 bar. Gauge at a volume of 0.2 liters. The fuel is then burned very quickly at constant volume before the piston begins its downward motion in the power stroke. The result of the combustion process is that 500 Kelvin is added to the temperature of gases in the cylinder. At the end of the power stroke, the piston cylinder has returned to its initial volume of 1 liter. What is the work done during the power stroke? That is, what is the work done from state 3 to 4? Let's assume that the air is very hot after combustion and that the temperature remains constant during the power stroke. Under these conditions, we can assume a constant temperature or isothermal process. Recall that the work done when a closed system's volume changes can be computed by integrating the pressure over the volume change. To evaluate this integral, we must know the relationship between pressure and volume. For a polytropic process, the pressure is related to the volume by P v to the n equals a constant. We've seen that in previous examples that for a constant temperature or isothermal process, the polytropic constant is 1. That is, that PV is equal to a constant. The ideal gas equation of state relates the pressure, volume, and temperature. PV equals mRT, where R is the specific gas constant. We see here that for our polytropic process, our constant is equal to mRT. Solving for the pressure, we find that P is equal to the constant divided by volume, which is equal to mRT over V. Substituting into the work integral, we see that work is equal to the integral from V1 to V2 P dV, which is equal to the integral from V1 to V2 of mRT over V dV. The mass, specific gas constant, and temperature are all constant for this process because the system is closed, and the process is isothermal. Thus, they fall out of the integral, and we're left with the work is equal to mRT times the integral from V1 to V2 of dV over V. We can perform this integral directly. The result is that the work is equal to the mass times the specific gas constant times the temperature times the natural log of V2 over V1. In order to evaluate the result, we must first know the mass of the gas in the cylinder and the temperature at which the isothermal process occurs. The problem statement tells us that the pressure, temperature, and volume at the beginning of the compression stroke are P1 equals 1 bar absolute, T1 is equal to 20 degrees C, and V1 equals 1 liter. At the end of the compression stroke, but before combustion, we know the pressure and volume. P2 is equal to 9 bar gauge, and V2 is equal to 0.2 liters. We can write the ideal gas equation of state for the states at the beginning and end of the compression stroke. P1 V1 is equal to mR T1, P2 V2 is equal to mR T2. Let's evaluate the mass at state 1. Solving for mass, we see that mass is equal to P1 V1 over R T1. Substituting our values, this is 1 bar times 1 liter divided by the specific gas constant, which is 8.314 kilojoules per kmol Kelvin, divided by the molecular weight of air, which is 28.97 kilograms per kmol, all times the absolute temperature at state 1, which is 20 plus 273.15 Kelvin. Looking at the units, we see that the kmols cancel and the Kelvin cancel, but we have bars, liters, kilojoules, and kilograms left over. We can get rid of the bars by recognizing that 1 bar is 10 to the 5th newtons per meter squared. We can get rid of the liters by recognizing that 1 liter is equal to 10 to the minus 3 meters cubed. On the bottom, we have kilojoules. We know that 1 kilojoule is 1,000 joules, and that 1 joule is equal to a Newton meter. You'll see here that the newtons cancel, the meters squareds cancel, and the meters cancel, the joules cancel, and the kilojoules cancel. And we're left with kilograms, where this whole term is multiplied right here. Evaluating, we get an answer that says that the mass of air in the cylinder is 0.001189 kilograms. Remember that we wrote the ideal gas law for both states at either end of the compression stroke. P1 V1 equals mR T1, P2 V2 equals mR T2. Note that for a closed system, both the mass and the specific gas constant stay constant throughout the process, and so we can solve for mR in each of these. Find that mR is equal to P1 V1 over T1, which is equal to P2 V2 over T2. We can solve this for the temperature at the end of the compression stroke. T2 is equal to T1 times P2 V2 divided by P1 V1. Remember, we must use absolute pressure and temperature when multiplying or dividing. Substituting, we find that T2 is equal to 20 plus 273.15 kelvins times 9 bar gauge plus 1 bar atmospheric to get an absolute pressure times V2 at the end of the compression stroke, the volume is 0.2 liters, divided by the pressure at the beginning of the compression stroke, which was 1 bar absolute, times the volume at the beginning, which was 1 liter. Note that here the bars and the liters cancel, and we don't need to provide any kind of unit conversion. Computing the result, we see the temperature at the end of the compression stroke, but before burning, is 586.3 Kelvin. The problem statement tells us that the combustion process adds 500 Kelvin to the temperature of our compressed gas. That is, that T3 is equal to T2 plus 500 Kelvin, which is equal to 586.3 Kelvin plus 500 Kelvin, or 1086.3 Kelvin. Note that the pressure must increase significantly according to the ideal gas equation of state. We can write the ideal gas equation of state for state 3, so the pressure 3 after combustion is mR T3 over V3. Substituting our values for mass and everything, we have that it's 0.001189 kilograms times the specific gas constant, which is 8.314 kilojoules per kmol Kelvin, divided by the molecular weight, 28.97 kilograms per kmol, times our temperature after combustion, which is 1086.3 Kelvin, all divided by volume at 3, which is 0.2 liters. We see here that the kmols cancel, the kilograms cancel, the kelvins cancel, and we're left with kilojoules per liter. We recognize that a kilojoule is 1,000 Newton meters, and that 1 liter is 10 to the minus 3 meters cubed. Now the liters cancel, the kilojoules cancel, this meters cancels, and you're left with newtons per meter squared. So P3 is equal to 1,852.81 kPa, where I left the 1,000 out and used kilonewtons. A kilonewton per meter squared is a kilopascal. We see that the temperature after combustion is the temperature at which our isothermal power stroke occurs. Rewriting our result from above to compute the work, we see that the work is equal to mass, specific gas constant, times temperature, times the natural log of the initial and final volume, where here we're going to sum final volume V4 over V3. These are the end states of the power stroke. Substituting our values, we have 0.001189 kilograms times the specific gas constant, which is 8.314 kilojoules per kmol Kelvin, divided by the molecular weight, 28.97 kilograms per kmol, times the temperature, 1086.3 Kelvin, times the natural log of 1 liter over 0.2 liters. You see here that the liters cancel, we don't need to convert them. See that the kmols cancel, see that the kelvins cancel, we see that the kilograms cancel, and we're left with kilojoules, which is a unit of energy or work. We find that the work is equal to 0.597 kilojoules.